Okay, so tonight we're going to be looking at our chapter on radicals. Now, technically all a radical in science is, or in chemistry, it's an atom with a unshared electron, as in one lone one. A very common thing that we see in maybe day-to-day life. Chlorine, like if we add it to our swimming pools as a cleaner, disinfectant, it gets turned into chlorine radicals. And two of them actually. What technically happens is we have that single bond between the two chlorines, and it breaks evenly or homolytically, where each chlorine gets its own electron, rather than taking all the electrons with it, like has happened in the past for nucleophiles and electrophiles. In this case, each substance keeps an electron. Alright, turns out in our swimming pools and other ways that we use chlorine, that is just activated by light, which you will see sometimes with the HNu abbreviation, which was Planck's termination. That was talking about a photon of light. That's where that comes from. Alright, so technically speaking, that halogen that we just saw, that chlorine, is going to be used to make this reaction happen. Now, this is kind of interesting. The halogenation of alkenes is about the only thing we can do with alkanes. Alkanes are relatively non-reactive. If you're ever given an alkane, an easy thing you can do is add a chlorine or a bromine to it. And you can do that just by a similar reaction to these. You take your alkane, you take your chlorine or bromine, and heat or light typically will do this, and it's just ultraviolet light, so it's not even, light from natural sources are going to be enough to activate this in most cases. And you can actually add well, you can do kind of a substitution. You'll replace one of your hydrogens with a halogen. Alright, but turns out light is necessary. If we try to do this without any light, the reaction is not going to happen. It can happen with heat. And what's kind of interesting, the light doesn't need to be continuous. So light is needed to start the reaction. Once the reaction starts, you go until you're either out of the halogen or you're out of the alkane. Alright, that implies a chain reaction. And that chain reaction is what we're seeing here. So our very first step is that homolytic cleavage that we were talking about on that first slide, where the chlorines get separated and we make our chlorine radicals. The next step is going to be a series of propagations. What that means is that chlorine radical is going to come down here and it's going to hit your alkane. And it will make the HCl right away. And now the HCl is what we see in the overall process coming out. But it's made during this first initial propagation step. Well, that creation of that HCl destroyed a radical. Well, that created a new radical. In this case, since we were working with methane, you made a methyl radical. And our second propagation step, we're going to take that methyl radical, let it collide with the halogen, create the other final product, the CH3Cl, and then a chlorine radical. And then this thing comes back up here, and we will just continuously repeat these propagation steps until we're either out of CH3, methane, or chlorine, Cl2. Or what could happen is if we have a situation where too many of our radicals build up, they might collide and neutralize themselves. If we have too much of our methyl radicals build up, they might collide and terminate themselves. And if these two build up, that's fine, because that's what we want. Now, these two termination steps should never really happen that much, because we're not going to have that many radicals floating around in here. So the propagation steps are the most common thing happen. So you'll use light or heat to create the chlorine radicals, or bromine radicals, and then you'll get these propagation steps where all of your alkane is turned into a haloalkane. Okay, those are always going to be your 3 steps. Now, there might be many more steps in each one of these, but you're always going to have an initiation step where you take a stable molecule and you turn it into radicals of some kind. Propagation steps always have radicals forming radicals. And there's typically at least 2 of these steps always. There can be more, but they're always going to have the same type of thing. You'll have radicals as both products and reactants. And termination steps typically have at least 1 radical turning into nothing, so a stable molecule. But you can typically tell where you're at based on where the radicals are created. Initiation steps always make the radicals, propagations make and create the radicals, and termination destroy the radicals. All right. If we look at bromine, we have a very similar mechanism. Still have 2 propagation steps on this because we are just putting a single bromine onto a single, in this case, ethane. And our steps kind of look the same. The bromine comes in and takes a hydrogen off the alkane, creating a radical on a carbon. That alkyl radical collides with another bromine molecule, making the alkyl bromide, and then creating a bromine radical again. And then we'll just repeat these steps over and over and over. Alright, now before we get anything crazy here, we want to talk a bit about the stability, because it's always been a factor when we're actually dealing with this. We do know that there are certain cations that are more stable than others, and there's certain anions that are more stable than others. And technically they were the opposite of each other. Tertiary cation was the most stable, yet it was the least stable anion. Well, the radicals behave closer to our cations, in the sense that our most stable radical is a tertiary radical. Now we will see that the allyl and benzyl figure into this, but we're going to get to those. We're not ready for those quite yet. Alright. And what I mean by that, that's going to help us predict what happens in this case. If I take butane and allow it to react with chlorine. Alright, so butane. Actually, you know what? Let's do the whole propagation step and everything. So what I mean by that, we'll actually assume that the initiation step happens and we make chlorine radicals. And then our very first step, we're going to have that chlorine radical attack the butane. Alright, but this one's a tiny bit different. So you see how I could make a radical off this end point and have this as a radical. Or my radical could be on that second one. Now the third and fourth are just repeats of these, so those are the only 2 radicals I would predict happening. Oh, and simply because those are the 2 radicals, my next step, where I actually now take my alkyl radical and let it collide with the chlorine, I would get either 1 chlorobutane or 2 chlorobutane. Alright, now predicting this, we do have one benefit. We just saw on that previous slide that secondary radicals are going to be more stable than primary radicals. So I do know that this radical is a little bit more stable. But I actually have 3 hydrogens that can come off this end or that end. How about I do it this way? I got those 6 hydrogens that come off that can create this one. So this was created by 6 possible hydrogens, yet this one's only 4. So is there some statistics going on? Is there a 60-40 kind of split based on that? Alright, turns out we do see this as the major. That predictability is a lot more based on that stability of the radicals themselves. Matter of fact, we actually have some pretty hard numbers that will help us predict it in any case. What I mean by that when we created these two radicals, we know there's a factor based on their stability related to that chlorine. And we get these weird numbers here. And we can use those to actually predict yields. What I mean by that, we're going to do that with this reaction. I chose one that's slightly more challenging. We're not going to do the full step. We're just going to try to predict all the products that are possible and then figure out what their theoretical yield would be. All right, so 2-methylbutane. All right. One of my products, and I'm just going to go right across that main backbone and put a chlorine on each. So I could rip off that very first. And technically, that could go here or up here. Those would all be the same. So there's 6 hydrogens that created this one. Or I could go to that middle position, which looks like it'd probably be the major product because it forms a tertiary radical. But there's only one hydrogen that could give us that. All right, our next one, go one more carbon over. There's 2 hydrogens that could give us this one. And then our final one, there are actually 3 hydrogens that could give that one to us. All right, now on that previous slide, these relative reates are going to factor in on this. So 5, 3.8, and 1. And here's how this goes. My keyboard froze up. All right, so this would have been a primary, so we're going to multiply those 6's by just 1. That's from a tertiary, so we're going to multiply that 1 by 5. The secondary is a weird one, because that wasn't a nice whole number. It was 3.8. And this, again, was 1, because those are primaries. All right, so that's going to give us a value of 6. This is going to give us a value of 5. This is actually 7.6. And just 3. Alright, now technically we could predict the major just from that. The largest of these numbers is the major product. So this one actually is the major. But if I wanted to actually calculate a rough percentage, which I can do, I could just add up all of those 4 numbers. And I bothered to start up a calculator just for that. So 6 plus 5 plus 7.6 plus 3 is 21.6. And then we're going to take each one of these and divide it by 21.6. And just to make this stand out, I'll change the color of this ink and I'll write the yields on top of this. So we already said this was the major. And how much of a major? Well, 7.6 divided by 21.6, about 35%. Which is not a huge major. 3 divided by 21.6, this is our lowest amount, only about 14%. Let's see, 5 divided by 21.6 gives us roughly 23%. And last one, 6 divided by 21.6, can be slightly higher at 28%. Alright, so we could predict our major product using those numbers, but much more important for us to realize, major is not that big of a deal anymore. We're definitely getting mixtures. All these are significant amount of products you're not getting a single product when we actually use chlorine. So radical chlorination, while it does work, it always creates mixtures when there's choices. So generally speaking, we're going to use chlorination a lot more often. Oh goodness. When there isn't a worry about too many choices. Like if I went with an alkane, a cycloalkane, all those are CH2s. None of them take priority over anything else. None of them are going to create mixtures, so we really only get one product. As long as we have one product, we could turn that into just about anything that we want. Alright, to help us out, we're going to actually... Whoa! Huh. I said my keyboard's messing up. It's really messing up. That was a page down button. It worked as an end button. Alright, turns out bromine's a lot more selective for us. Matter of fact, we don't even need to use those numbers up there. 1600 to 82 to 1. If you actually bother to calculate it all out, you're going to find tertiary is far more likely than secondary or primary. So if you actually were to take butane and react it with bromine, even though there's two possible radicals that could form, this one's 82 times more likely to form, and that's basically guaranteed to be the major product. And even if we went back to that 2-methyl butane, you're going to get the 2-bromo-2-methyl butane all the time because it's going to go to the tertiary location. Bromine is far more selective, and that really pays off a lot in actually predicting the products. Alright, so why is it that big of a deal? When we look at both steps of the reactions, so creating the radical, both creating and destroying it, so both steps of our propagation, and we compare them, chlorine and bromine, we see that the first step with regard to chlorine is an exothermic reaction, yet it's endo with bromine. That first step on the bromination is an endothermic step. That pays off tremendously because we're going uphill, and this is a far lower hill for us to go up, so it will require less energy going into it. Yet since all three of these are more stable than the original starting ingredients, they're all favorable processes. Or when we look at it with our nice little coordinate diagrams, we have these little tiny hills with our alkane and chlorine. So all are just as likely. There's very little difference in the activation energy, so they're all just as likely to make it over that hump. So we see all of these. We do see the tertiary more often, or it's more stable, so it leads to those mixtures. Yeah, if we go over here to bromine, since we have to put so much more energy in, we almost always end with the one that requires the lowest amount of energy, tertiary, or secondary if there is no tertiary available. Alright, that's bromine and chlorine. What about iodine and fluorine? Well, fluorine we avoid. It's so darn exothermic, this is a huge amount of energy. In this actual process, there is even a weird chance where this fluorine could get in there, and if this was like an ethane or propane, it actually might separate a carbon-carbon bond. It's just a little bit too reactive. It has caused explosions. So no one really does that. Iodine, on the other hand, is so darn endothermic that it makes it nearly impossible to go this route. It's so much easier to put an iodine onto our alkane with just an SN2 type reaction with any of our substitution reactions with an already haloalkane. We knew iodines were more reactive in that chapter anyway. We could actually have an iodine replace a chlorine if we wanted to, and it would actually happen far easier. Alright, now I did just mark this out. That's not entirely true with regard to fluorines. Your book doesn't really talk about it, but we actually can put fluorines onto single, we can make alkyl fluorides, and it is through free radicals, and it typically starts with a carboxylic acid, and our source of fluorine is xenon difluoride. And this will indeed, through free radical halogenation, put a fluorine onto that R group. It's outside of our chapter. It's kind of a new discovery. I shouldn't say new. I learned about it ages ago. But it is a way of doing free radical fluorination. But it's outside the scope of your textbook. Just figured we'd add that now. Alright. Next thing we're looking at is other things we can do with our radicals in general. So we'll get away from the free radical halogenation and just look at what radicals can do for us. Alright, so on top there I have an alkene reacting with HBr and given a very predictable Markovnikov substitution. The hydrogen goes to the side with more hydrogens, bromine goes to the side with less. Alright, that was very predictable. That's definitely an alkene thing. Well, it turns out we can manipulate that. If we use peroxides in there and just have some peroxides floating around in there, we end up getting the anti-Markovnikov, where the bromine ends up on the hydrogen with the more the bromine ends up on the carbon with the more hydrogens. Now the mechanism here will help us see what's going on, because what actually happens is our peroxide creates radicals. Now go to peroxide, and we actually can always write ROOR, and I'm fine with that. So instead of peroxides on here, if you were to just write ROOR, you're going to be perfectly fine. You will also see a little bit more common, where they will write out what R groups they are. Now, this is a tert butyl group. You will sometimes see this as TOOT. Tert butyl, OO, tert butyl. Toot. That peroxide is the important thing. Now, it's just that OO bond. Having R groups on there make it a little bit more stable in this, and it helps the solubility. That's typically what will change. But as long as we show that ROR, or OOR, separates into those radicals in our initiation step, and then we see that that initiation step actually does indeed collide with our HBr to create a halogen radical. So unlike our alkyl halides, we have two initiation steps on this. Now, propagation step, there is still two, but this time the bromine attacks the double bond as a radical while the double bond attacks. Because remember how we always had the arrows go with where the electrons attack? Well, in this case, one of the electrons that make up that pi bond attacks that one lone electron on the bromine to make the bond. That's why they have the arrows going two ways. And that creates a radical. But the reason we end up seeing the bromine on the end is because we would like to create a more stable radical. In this case, it's the secondary radical. Our second propagation step, that radical is going to attack another HBr, and we'll make our final product and create a new bromine radical for a second propagation, or an additional propagation step. Alright, so generally speaking, our termination steps are only ever going to have to, the only ones that we're probably going to see too often are this one, because we might have too many bromines, but we would never expect to have too much of this stuff building up. So these other termination steps are going to be trivial amounts at best. Alright, so generally speaking, we can say that if we use peroxides with our HBr, we're going to actually get that anti-Markovnikov product, and we don't have to worry about rearrangements. Which will be very nice, because without the peroxides, if you remember this one, so if I just did that without peroxides, it creates a cation, and it would have created the most stable cation, but this thing can hydride shift, and you would have ended up with mixtures, but your main product would have had the bromine down there. So you wouldn't even have gotten it anywhere near where that double bond was, at least not the major product. But peroxides, creating those radicals, we don't see hydride shifts on that. Now, something we have to worry about with peroxides in general is the certain ones actually can react with themselves, and what mostly you need to worry about is if you have a given peroxide, ROOR, that type of thing, you need to worry about, how about back that up? If we have an ether, and you happen to have an ether that has a CH2 next to it, so the alpha carbon has a pair of hydrogens on it, it actually can create a free radical. And those peroxide radicals create these proxy acids when they're all done, which actually can cause problems. Now, problems being they actually can form explosives. Something we have to worry about with diethyl ether. As that stuff gets old and ages, it actually reacts with itself and forms peroxides. Alright. Fortunately, the peroxides, or unfortunately, depending how you want to look at it, the peroxides only change the products with HBr. If you try HCl or HI, you get the product you'd expect. And it really is because of how the reaction goes. It is based on the fact that the bromine is always an exothermic step to create the radicals, and yet on chlorine it's exothermic the first step but endothermic the second, and iodine it's endothermic first and exothermic the second, and both of these endothermic steps create a situation where just straight adding it across the double bond is more beneficial. So our pathway to standard HCl addition across double bond, or HI across the double bond, is easier than creating that radical. Alright, we do have to worry about stereochemistry here. Matter of fact, if I go way back up here to our the ones that we predicted, where we actually did our math, this particular one that I said is our major product, well, if we look at it, that particular location would be a stereocenter. And when that radical is created, it does look kind of like a carbocation, so that chlorine could have went on either side. So we do get R's and S's. And that's what it's talking about here. Our radical, whenever it's created, and we're talking about in this case, we're talking about that radical, that particular radical would actually be properly set. It's like an sp2, so trigonal planar in its shape. And because it's because it's trigonal planar, when that bromine comes in there from our bromine, that second propagation step, it could attack on the top or the bottom. So we always get enantiomers here, and we are expecting it to be a perfect ratio, so we are expecting this to be a racemic mixture. Equal parts R, equal parts S. Now, if we're doing it with that peroxide, something like HBr, same type of thing happens because we do create that radical. The bromine can go on either way. It goes onto that end with more H's, but on that, when the bromine goes on, it creates a radical, and that radical allows for us to come in on the top or the bottom on that second propagation step. So we always get enantiomers. All right, and that's just drawing our how we view it. So we have our p orbital has the radical in it, and on our step where the bromine comes in, it could attack either side. Okay, going to add to our stability here. I mentioned this earlier. We have to add in our allylic and benzylic as well, because it turns out they follow the same trend as they did with carbocations. Allylic radicals and benzylic radicals are more stable than a tertiary radical, but they have slightly different reactions going on. Alright, what I mean by that if I actually take a halogen and actually use my heat or my light, I will see I can get free radical addition to the benzylic or the allylic position. This would be very easy to predict based on what we just saw. Those radicals that would have been created in those propagation steps would have been very stable. So we wouldn't have to worry about any mixtures here going on. Alright, we do have a problem though. Along with this, we have some competing reactions. What I mean by competing reactions, this halogen can't really do too much here we have to worry about, but on our allylic product, suddenly this gets attracted by those halogens. We could just do straight addition across that double bond. So if I had too much of this, the straight halogen, I'm going to ruin the double bond. So having X2 is a bad way of doing this. It allows the possibility where our double bond will react. Alright, so what we're going to do instead, to avoid those competing reactions, we're going to actually use a different source to create our bromine radicals. And we're going to use this stuff, which is perfectly fine to abbreviate as NBS. N-bromosuccinimide has this wonderful ring with a single bromine on it. Well, if I react that with a cyclohexene, I do get free radical halogenation only. I don't have to worry about, if I were to do this with just straight bromine, I don't know why I did that as a superscript, and HV, I would get this stuff, but I'd also get where I just add across the double bond. So instead of having the double bond, I have a bromine and a bromine. Alright. Best way to avoid that is to not use bromines when we're dealing with something that has a double bond in it. So NBS, N-bromosuccinimide, along with the light, will actually create enough free radicals of bromine that we can actually see this happen. And we don't have to worry about any addition reactions. Now, its mechanism is kind of neat. It's I'm out of, I got a kind of a odd order here. Turns out we are going to create our bromine radicals from that N-bromosuccinimide. When light hits it, it creates a small amount of bromine. And those radicals would then attack our ring, create a radical and some HBr. And then that would attack another bromine and add it across and then recreate our bromine radicals. Alright. Now, some considerations here. When you are dealing with allylic, we can get some resonance. Even though we never expect rearrangements with radicals, and we do with cations, we do see that these move around. What kind of happens, instead of actually fully trying, this thing drops down here, and this one comes over here, and that makes a new bond, but it leaves this one off by itself to create a new radical. So it looks like the double bond and the radical swap places, and that's kind of what happens. It is a weird pi system. It's got those 2 electrons and 1 electron in it. So it's got 3 electrons in the pi system. And it resonates back and forth. And those resonance contributors are where those bromines attack. So we could get bromine on the end or on the middle. Now, typically, and I will say typically, I'm going to ask you this question. I want all products. I will not be asking too often what the major product is. Because while typically it's true, the alkene controls the major product, and since that particular alkene only has 1 hydrogen, you'd likely predict major. But that's not the only thing that happens here. Now suddenly, what steric hindrance we have with the bromine sometimes makes that harder to form. So our major product is not always clear-cut. When we're dealing with allylic positions, we're actually just going to be looking at what mixtures we end up making, or what products we end up in the mixture. Alright, one of the last things we introduce in this chapter is multi-step synthesis, which means we're going to make molecules using all the reactions we've actually introduced up to this date. So things now, some of these are going to be things from previous chapters. Matter of fact, everything that we're going to do on this particular multi-step synthesis have absolutely nothing to do with this chapter. That's all old stuff. Alright, now when we do multi-step synthesis, there's some thinking of going backwards, sometimes we go forward. What I mean by going backwards, this right here is an aldehyde. And if I told you right now that you can make it, with what we currently know, that helps a lot, because there was really only one reaction we have used to date to make a aldehyde, and that was using PCC. Because if you think back, we used PCC on alcohols. And if I used PCC on alcohols, it removed one of these H's and removed that H and created that carbonyl. But it didn't oxidize this all the way to an OH, so that's how we knew it was PCC. Alright, that's what we mean by, on this multi-step synthesis, sometimes working backwards, because there's not many things that we did with all these components. Matter of fact, even on the other side, there's really only one thing we did with ethers so far, and that was to react them with something maybe like HI, because what we would find happens there, CH2, because that's a CH2, this would be an OH, and this methyl group ends up with that I. And technically, we'd actually want this to just be a 1-to-1, so 1 equivalent, because if we did this with excess, this would also get turned into an iodine. Alright, but if you look, HI creates this alcohol. The alcohol is what we want to make our final product. So the nice thing is, if we break it down and look at what we know is possible, that gives us a starting point. There's some things we don't necessarily want to start with. Alkenes, there were too many things we learned to do with them. So there's a strategy here. We're going to find what step what can we identify as a step that has very limited things we can do with it. Alright, and this next slide just has that written out in a little bit more detail. Alright, there we go. Got our HI, a little bit of heat, creating the alcohol. And instead of using PCC, our book was using the NaOCl at 0. Does the same thing as the PCC does, but it's a little bit safer for the environment. Alright, let's try another one of these. Not that one. This one. Alright, we are going to somehow turn this alkane into an alkene. It's actually a dialkene. Alright, but can't do that directly. Let's think about what we know we can do. There's plenty of ways we could do eliminations and make an alkene, so let's not try to focus on what we did there. What can we do to an alkane? Well, this is this chapter, and there's only one thing we've really learned we can do to any alkane. If I take chlorine and I take some light, I can make an alkyl chloride. Alright, that gets us started. Now we can do something with that. Alright, we know we want to make an alkene. Can I make an alkene out of this? Well, yeah. If I just do OH and some heat, that would favor an E2, and I can make it into a single double bond. Alright, but we want 2. Now you might think, well, let's just do this again, but remember, this is a double bond. It might add across that chlorine. So what did we do if we wanted to add another halogen to an adjacent location for a double bond? Yeah, we use that NBS stuff. And now, that N-bromosuccinamide didn't just put chlorine on there, it was specifically a bromine. But it did put it in the allylic position. And then how could we eliminate that? Guarantee Ne2? Well, OH and heat again. Matter of fact, it wouldn't even really require that much more heat because it would be excuse me, that double single double. So it'd actually be a favorable process. Alright, let's see how I did it, or how it was done from your book. They did the first step with bromine. Same type of reaction as ours did, because there was no real need to actually be specific there. They used tert-butoxy, but I used OH and heat. The heat's going to help us favor E2. This will actually guarantee E2. So that might be a better way to guarantee you're going to get nothing but elimination. Then there's our MBS and some peroxide to get the bromine there. And then just do another elimination to get to our conjugated system. Alright, let's try another. Ooh, a little bit more. Okay, seems more complex, but let's break it down to what can we do. Alright, I do know there was only one way of putting bromines there and there, adjacent to one another. If we put them all in one step, this had to have been something like so. Because if it was like that, we could do bromine and do that halogenation. But I don't want to actually rely on that because we have more than one way of putting a bromine on there. So that might not be the best side to start on. Alright, but if I start over here, I do have a slightly better way to start, because this is an alkane. And there's really only one thing I can do to an alkane, and that's put a halogen on it. Alright, I'm going to specify bromine in this case. And why is bromine far more important than just chlorine? Now, because chlorine could add to any of these CH2s, could add to that CH3, it could add to this CH. And we're going to get all those. Now, we could figure out our yields based on those little predictions, but if I use bromine, I don't have to worry about that. If I put bromine in there with my light, it's going right there and only right there. Alright, why is that important? Well, I just did have drawn up here that I wanted, it'd been nice if I had this, because I can just now do that bromine, and I'm going to put carbon tetrachloride in with that bromine, and I would have ended up with them being trans to one another, just like this is drawn. Alright, but do I know of a way I can turn this guy, this haloalkane, into an alkene? Yeah, but that's just an elimination. Now, I definitely don't want to use tert-butoxy here, because if I use tert-butoxy, it's probably going to put the double bond out on my substituent. So I do want that Markovnikov product. So I'm going to put it out there instead. And let's see. What did we do in the book? Alright, there's our bromine. And they used slightly different base, OCH3. It's not bulky, so it's going to guarantee we get that there. And then there's our bromine, and they used methylene chloride, but it does the same thing, or something similar. All right, and our last one. Oh, answers are already up there. All right, well, this guy is an alkane. There's only one thing we can do to any alkane, and that is add a halogen to it. But since this is benzene, any radical we're going to create is right there. So the only potential halogen we could create, or haloalkane, is that guy. Well, that's good, because we can just do a straight elimination there and get this nice little conjugated thing. Alright, now, I would like to have something added to this outside, so I can end up attaching that in a substitution type reaction. So we're going to use HBr with some peroxides, and that'll put the H there, or they'll put the bromine here, and then we'll add an H at that location. That does get the bromine on the outside, and then it's just a straight SN2 to put that nitrile on the end. Alright, now, spent the last part of this chapter on these multi-step synthesis. This is a big thing starting now, and all through the rest of our rest of this semester and all of Organic 2. Going to be a lot of multi-step synthesis. So knowing all the reactions that you have seen and know how to use them is very important. So do practice your multi-step synthesis. All right, have a good evening.